sound. You should see it there. Okay, everything is there. I think that we can start. So, thank you everyone for attending my lecture. This will be the third lecture of our Erasmus class. I have one slide that is the same that Professor Christian Jambrovi showed already. So, first of all, you know already which are the two partners of this Erasmus class. So, from Italy, the Consorzio Cultura e Ricerca, and from Zagreb, the university. I cannot read in Croatian the name anyway, but this is what you already know. Just one slide regarding the program of our Erasmus class. My lecture will be number 3, so I will talk about the equipment, and before starting speaking about the equipment, I will give some words, about the theory of what we are going to measure, so the impulse response mainly. And I will speak only for 40 minutes this morning until 1 p.m. because we are a little bit late. And then in the afternoon, starting from 1, we will move to the other room on the upper level to make some practical work. So we need to mount everything, the microphone, all the audio system to make the measurement. So let me start from the beginning. So what we are going to do during our practical lecture, practical part of this Erasmus class, especially tomorrow. Tomorrow during the day, and also tomorrow in the evening when we are going to be to the concert course. We are going to measure something that is quite important, that is the impulse response. The impulse response is a parameter, scientific parameter, that is very similar to the reflectogram that Professor Jambrosic described during his lecture, but has a particular mathematical significance, meaning. Because we have to consider that in acoustics we have to think about the room like a linear and time invariant system. This is quite important for us from a mathematical point of view. What does it mean this? It means that when we try to clap like this, we believe that the behavior of the room is linear, so it's not adding any particular harmonic distortion, just to speak very clearly, and also time invariant. So it's not changing during the time, especially when we are going to make the measurement. This is quite important. This is the theory. Then, what does it mean, the important, why I told you that impulse responses are very important? Because if you have a room like this rectangular, you can see my mouse, and let me try if I change this. No. So I want to avoid this. I want to change the setting because I knew that sometimes when we want to, no. I am going back to the display setting that normally I use because this is a problem with the pointer. So this should be the display setting. No. Yes, I want to duplicate because this is the only possibility that I'm sure that we see also that. Now you can see the pointer, good. So, yes, here, not here. Now you can see, okay, good. So, if you have a rectangular shape like this, if you are going to put some signal inside, both in frequency and time domain, what does it mean frequency? Frequency means something that we normally already understand, some sound with some frequencies. In time domain, it means just a waveform. So, for example, music or speech or something similar. The black box, something that we don't know anything about it, will behave in some specific way. So it's changing the signal going inside, and we have some output. That is what Professor Jambrosic showed before when he played some musical example. So So we have some dry music, so without any kind of reverberation. We can add the reverberation because we know how how is the behavior of the black box, and we get some results. The calculus that we are doing is called convolution. It's a sort of multiplication. It's a very particular kind of multiplication, but it's just an algorithm. So we have some signal going inside, we apply this algorithm, we must know the input response, and we get the result. This is how it works. But the main question is why we can believe, you can assume that the room, the auditorium, the concert hall is linear and time invariant. Time invariant is very easy to understand because we believe that nobody is changing anything inside. For example, nobody is moving some acoustic panel, is moving the ceiling, is moving the sound sources because we are making the measurement, everything is steady. Nobody are opening or closing doors. Nobody are opening or closing windows exactly in the time that we are going to make the measurement. This means time invariant. But linear is something that comes from the theory of acoustics. Because when we are studying acoustics, acoustics is a branch of fluid dynamics. This is the reason why I'm normally teaching fluid dynamics, heat transfer, but I'm also studying and teaching acoustics. Acoustics is a branch of fluid dynamics in which we have to make we have to assume some hypotheses about the fluid, the air, in which the acoustic phenomena happens. The fluid must be ideal, so without any kind of thermal dissipation, must be homogeneous, so there are no positions in which we are lacking of fluid, must be isotropic, so every path has the same importance, has no relevance the weight of the fluid, I mean the density is constant, at least in the room in which we are making the measurement of the performance, and the most important aspect, and that must be linear. Linear, it means that the global pressure, that is the phenomenon that normally we experience when we are going to speak about acoustics, is simply the sum of the acoustic pressure that we have normally here, that we normally use and we measure by means of barometer because we are considering the atmospheric condition in the environment, plus the acoustic pressure. So this expression is linear because the result is simply the sum of two different elements. It means linear fluid. So the theory told us that some scientists in the past developed some formulas. This is the formula, but the name is the wave equation that Mr. D'Alembert wrote and discovered more or less 2 centuries ago. So this is the theory. So the most important aspect is to remember that the acoustics must be linear and time invariant. I already showed you during my first lecture what happened inside the auditorium. We saw also other very nice movie during the previous lecture, but already I told you that we have normally the direct sound. So if this is the position of the sound sources, if we have the receiver in this position, the direct sound, it means that a very, very, very short, theoretically, without any duration of the sound, because the clap, when we think about the clap, we suppose that the clap lasts only an infinitesimal time, so something that has no basis in the time. So when this clap is traveling, we got the direct sound and all the reflection. We heard that ETDG, ITDG means initial time delay gap, so the difference in time between the direct sound and the first reflection, for example, from this position on the ceiling. Then we have several other reflections, like this, a third one, maybe double reflection, also from the floor, and then we have several other parts. But remember one of the most important aspects, that is, we haven't only the positive element of the pressure, because it should mean that there are not steady acoustic field. When we have moved in the air, we must have a complete oscillation, movement, like a pendulum, not only one direction. So we have always also the negative part, so because it's necessary to have a complete period. So this is the theory, but the reality is that we have an image like this one. So a direct sound, early reflection, strong reflection. We know that if this delay is too long, for example 40 or 50 milliseconds, it will become an echo. Some people can hear echo also a lower time delay. It depends on our hearing capability. Normally speaking, we say 50 seconds. And then we have strong reflection. Normally we can see the strong reflection and the reverberant tail. The reverberant tail means that reflection are mixed together, the second order with the fifth order and so on, so there are several overposition of different reflection. This is the meaning of the impulse response. So remember, this most important aspect is that if we assume that the room is linear and time invariant, our experiment, that is to play some signal which has a very, very low duration, so an infinitesimal duration, theoretically, mathematically speaking. If we play the sound and we record the sound in other position, we got this reflectogram, this impulse response. Reflectogram is something that is practical, what we acousticians consider. But the people working in mathematics, they consider this parameter quite important and they call impulse response. Normally, we measure impulse response several times in our life because this is what we normally do always. When, for example, we want to tap a table, because it's similar to the impulse. And when we tap the table, we get some sound. If we tap a chair, another sound. If we tap some glasses, we have a different sound. So you can imagine that this clap, this tap of a clapping, it means that it has some importance for us. I reported some example. Normally, the restorator, people working in the restoration preservation of ancient buildings, they used to hit with a hammer what happens in the walls to understand if they are stable or not. We can also hit in the fruit, in the watermelon. Maybe our grandmother, grandfather, they normally used to crack on the watermelon. We are coming from Emilia Romagna region. We have the Parmesan cheese. The Parmesan cheese, we have people hitting with the hammer to understand the sound, if it could be sell or not. The flask that I was mentioning before, in order to understand if fresco or the plaster is stable or not. The glasses, I have the glasses here, but if you want to click like this, you can hear a different sound, and normally you can understand if this is normal glass or crystal. Maybe coming from the Wiener region. It sounds very nice. So the most important aspect is that, going back to the picture that I showed you before here, if we are able to obtain the impulse response, we can make a virtual perception of sound because we put something inside, we apply the effect of the room in order to obtain the outcome from the room. This is the theory. This is really the theory because our colleagues working in electronic, electric, informatic engineering knows very well this theory. Knows very well because they apply this theory for some other system, not acoustic, but other field. But also our mechanical engineer knows this problem. They have different problems and they know very well that this impulse response for linear time invariant system are quite important. Let's go back now to my slide because I want to tell you that this possibility, the possibility to measure properly with the highest possibility, highest technology, and highest scientific theory, will allow us to understand exactly how the room will behave. This allows us to listen the effect. It is quite important for us because we are working in acoustics. So we prefer to listen to sound instead of watching or seeing picture or see number or see other kind of data. musician wants to listen to music, not to see a report, written report, number, graphs, or maps. This is important. I mentioned that it's similar to the wine. Why to the wine? Because in my field, in my knowledge, is the only aspect in which people are describing wine with very complicated sentences. I can smell particular how something Versailles of, I don't understand the meaning of smell. I can see some particular colors, I don't know. I think that the best solution should be to taste. If this bottle of wine is 2,000 euros the price, can I taste? I know that I'm drinking 100 euros, but what to taste? Not to see or to read a report. Exactly the same for the acoustic. We should teach to the people that the best solution to understand the acoustic is not only to see a report, but to listen to the music. And this methodology allows you to listen the effect of the room. So, what is our target? We have only one target. I have to tell you, in room acoustic, we have only one target. That is to measure with the highest technology the impulse response. The better will be the measurement of impulse response, the better will be our knowledge of the room, of the acoustic of the room. There are no other tasks for us. No other, we are looking nothing else, only this. Which are the possibilities that we have to measure? This is the target of my lecture of today, this morning, and also for the afternoon. The easiest method is the clapping like this. Which is the problem? First of all, the clapping are very different each other. We have to learn how to clap, because if I clap this, it's different from this. So how can you imagine that you are able to understand the acoustic by clapping? You have to learn how to clap. This is good. It's not. This not. So you can imagine the repeatability of this measure is very low. But even if it's very low the quality, we could have an idea, because all musicians, when they went inside the room, they clap. And they, because they understand from the clap, because also they know how to clap. They are not clapping this way. It's different. So they know, and they have an idea, at least in the medium frequency, the medium range, from 250 and 1000 hertz. More or less, they have an idea. Of course, this is the easiest method to get the impulse response. Remember also the meaning, what I told you, impulse response. So the response of the room to the impulse that we are going to play. Also the parameter, the wording is important. Impulse response to the room of an impulse. The clapping is the easiest way. We have also the clapping machine. This is just one step more. The clapping machine, it means that we have two different materials we can put together. We can also improve this clapping machine, maybe adding some cavities inside in order to be able to have an impulse response working also at more or less low frequencies, because if you have a cavity, you can increase the low frequencies and have a more a better idea about the room will sound. And this is what it was done in the past, just because this method has a lot of quality for us, because, for example, for traveling, it's better having a clapping machine instead of this equipment that we showed before, and we show later. Other methods are to use balloons or pistol shot. This is what we made, maybe the balloons. I have to tell you that also now some people, in some particular case, we can use balloons. Why? Because balloons is very easy. You can buy with no money, it's very cheap. You can just blow inside, maybe with some mechanical method, and you have just the possibility to bank the balloons, and you have very strong impulse response in very short time. So very similar to the real theoretical impulse. Also here in the past, several people make different comparison, large balloon, little balloon, large balloon works at low frequency, little balloon not so low frequency, and so on, but this is a very easy method. Pistol shot. Pistol shot is a method that I used when I was a student. When I was a student to the master engineering, I used to to shots with a pistol in several theaters because at that time it was the easiest method to make measure without equipment. I made a measurement in Venice, maybe I told you during my first lecture, in the Theatre La Fenice before the burning. You can imagine in Venice it's not easy to bring all the equipment, all the bridge. So it was very easy for me to have a pistol shot, just a digital audio tape, in a microphone binaural in my ears. One guy played the pistol shot, I was recording, really easy. Nowadays, it's completely unfeasible to travel with a pistol inside your back because it will be stopped immediately. You can imagine, very completely unfeasible. But it's one possibility. Other possibility is to use the firecracker. So, I'm happy to have this video. This video is quite old because I remember that we recorded this video, it was in 2011, more or less, so 14 years, but I left it alone. First of all, because it's the only example that they have of firecrackers, first of all, so I had no other possibilities. But the reason is another one, because these measurements were done inside the Apidarius Theatre in Greece, one of the most important Greek theatres. So let me play this video. Where is it? Here. You should see.
Non si vede, non si vede.
Again, let me see. I want to stop first of all. Okay, why can you see? Let me see here. You should, no, still you don't see. Now you see from here. Let me see if now you see. Yes, okay. Yes, because I had to move because I will not. Oh, okay, now I can see. Okay. So give a look. This is the firecracker. It was not allowed to put in the middle here, but at that time I remember that I was this one on this floor. I was recording with the Brahma microphone. You can see this effect due to the diffraction of all these seeds, and so you can hear this particular effect of impulse response. Okay, so this is the other possibility that we could have for the method of measurement. But apart this, all these are direct method to measure directly the impulse response. Why I told you direct method? Because we are playing the impulse and we are recording the response of the room to the impulse. But from a mathematical point of view, this works. But from a practical point of view, it's unfeasible. Why? Because as I told you before, the duration of the impulse should be nothing. This is the theory. It's exactly like when you, I believe, to the primary and secondary school, your teacher told you, please write I don't know, a line. You draw a line. And your teacher told you, this line has only one dimension. I raised my hand and told to the teacher, excuse me, it has some thickness. No, you have not to consider the thickness because you have only one direction of the road. And I told him, but no. He told me, you should try to write with no thickness and imagine to try no thickness of the road. This is the same. When you want to play the impulse, we should play in a very, very short time that should be equal to 0. So if we try to play, for example, open a waveform with this direction, I want to check here, you will see that there are no possibility. For example, I can open one of the software for doing this audition, and again, I need to equalize, otherwise you can't see. Let me see when you see and when not. Now you see, okay. For example, if I generate here a silence, from a theoretical point of view, I could also increase the sample rate. I don't know if you know the meaning of this parameter. Maybe people that is going to normally record know the meaning. If, for example, I could create an impulse very easy in this way. I zoom, zoom, zoom until I see the single sample I put here. You could tell me, oh, this is a perfect impulse. I put a perfect response. Impulse. It looks like this is perfect impulse, but if I play, nothing. Why? The duration is so low that you cannot hear. So this doesn't work practically, even if the theory say that it works. So you need to use a different method that are method based on alternative method and the so-called not direct method, so indirect method. There are two, or the most important indirect method are two. One is to create and to play the maximum length sequences. So a pseudo-random noise, similar to the white noise. I know maybe you know what the meaning of white noise. Something like shh, this is white noise. And you should compare what you are playing with what you are recording, and by comparison, you obtain, with some mathematical calculus, the input response. This works. This is the method that we used until more or less 2002, 2003. But even it was not able to separate non-linearities that are not belonging to the room, but are belonging to the equipment. Because remember that when we are going to make the measurement, we measure everything, the room, together with the sound quality, so the frequency response, or the input response, or the microphones. Because also the microphone has a frequency response, not only the room. So we must be sure that we are measuring the acoustics of the room and not the acoustics of the microphone. We have to separate the electronic system from the acoustic system. And this is the reason why we abandoned this method in the past. Because the non-linearities are included. And normally we developed, by the way, we had a pattern in which we were able to separate the non-linearities. Now I want not to show you to lost my time, but we can separate these non-linearities. Which is the method that we normally use instead of MLS, is the exponential sine wave. The method that normally we started maybe in 2000 to use this method, but not only we. I think that all the world now in acoustics uses this method that was invented for Professor Angelo Farina 10 years ago. One of the most important things that still and will exist for the future. This is the formula. We will play this afternoon. I'm not going to play now, but what we are going to do now, we need to do, and I'm going back to the formula at the beginning, because this is what we are going to do. So, as I told you before, this is the so-called black box. Black box, it means that we don't know anything. Could be whatever you want. We don't know anything about this black box. The only thing that we know is the input response. And the theory tells us, if you know the input response, you know everything. Something that is unbelievable. So we don't know anything about the room, but if we know the input response, we know everything. So if you have the input responses, the theory says you put some signal, you have some output, and this output, this is the formula with this asterisk, is simply calculated by means, what happened? Zoom, I have a problem with Zoom. I hope that we'll be able to still record. I think that I messed the connection with Zoom. Because I don't know what happened, they put me out from the Zoom meeting. So I don't know, you can see because, but no, I have a problem now. And not connected anymore. problem because it's stopping me for the video. Yeah, you have a calling. Okay, at least this one. We have a plan B.
Yeah.
Good, good.
But this is live, obviously. Let's see now.
No, I cannot find. Not internet.
I check myself.
Okay, that's why. We are wasting time, so I am going back with my presentation. So what we are going to do now, I'm unable to connect. What we are going to do now is, as I told you before, we know the behavior of the black box because we know the input responses. So the output is simply this product, this multiplication between the input, what we are putting inside, and the input responses. This product is called convolution. This is the name. So the problem should be, if we know that the output and we know the input, could we calculate the input responses? If this was simply a product, we should divide the output with the input to obtain the input responses. It's very easy. The problem is not so easy to divide the output with the input by means of convolution, because convolution hasn't the possibility to divide. We can also make the product. So if you are not able to divide a number with another number, how can you do? You can multiply with the inverse of the number. This is the trick that we have. So instead of divide the output with the input, we take the output, we multiply with the inverse of the input, and you obtain the input response. This is the method that we will do this afternoon and also tomorrow for the measure. So the input response is simply what we record with all the equipment, multiply, so with the product, convolution product, with the inverse of the signal that we are going to play. The inverse of the input response, of the exponential sense wave. What does it mean, the inverse? The inverse by convolution means that the convolution we did between the exponential sense wave and the inverse filter, we get what is invariant for the convolution, so the impulse. Exactly the same for the product. If you have a number, 3, you multiply with the inverse of 3, 1/3, what you obtain? 1. Why you have to obtain 1? Because every number multiplied with 1, we will get the same number. So see, this is the invariant for the product. For the sum, which is the invariant? 0. Why? Because each number, sum, if you make a sum between each number and 0, you obtain the same number. For the convolution, the invariant is the impulse. Why? Because any signal going inside the room, if you have only direct sound, you get this exactly the same sound that you have put inside. So the control to know if the inverse filter is really an inverse filter of the signal that you are playing is to make the convolution between the two signals. I want to show you, if I'm able in the last 2 minutes to show you this, because I will open the same software before. I will generate one sine sweep that will generate like this. Okay. Can you see what is written here? Not really, but I will read for you. The inverse filter has been stored in the Windows clipboard. So this is the signal. This is the inverse filter. And if I make the convolution between the two signals, effect. The convolution is very easy to do. There are several possibilities. No. Convolve with clipboard. What you will obtain? A delta. And you cannot see, now you can see. No, it's too little for the, I have to increase to zoom, otherwise you cannot be able to see. This is the impulse. So this means that the exponential sense wave convolved with the inverse filter you will obtain the invariant, so the delta. So our procedure for this afternoon will be this one: to mount everything, to play the exponential sign sweep, then we will get the output, so we will get from the microphone the output, and by means of convolution between the output and the inverse filter, we will obtain the input responses. What about the measurement, and what about the equipment? I lost maybe the PowerPoint due to this problem with the connection. These are the equipment that we have. You can see here in front of me. I have all this picture in which I use this equipment. I already showed you, I believe, during my lecture last March, but you can see here all the instruments that you have in front of you. So, a dummy head, this one, that is able to measure input responses on behalf of a human head, because we have two pillars, there are two microphones inside, and it's very similar to the behavior of a human head. Then we have this one on the top of the dummy head. We have unscrewed the screen, so you can see 4 capsules, 4 microphones. This is yellow, like a gold color, you can see, like tetrahedral shape. This is able to capture the sound coming from 4 different directions. It will be able to measure, to calculate the input responses, so-called ambisonic format. Then we have another microphone, this one, you can see this like a sphere. This is called Egen mic. This Egen mic has inside 64 microphones, 64 channels. It will work in the protocol called Dante, I will show you in the afternoon. And this is able to capture different input response, not only one point, but coming from different directions. Because the theory has a lack inside. So, because in the theory, the microphone is like a point, but we are not a point. We are a real person, a real man. So we want to pay attention also from which direction the sound is coming. So we want to have the possibility to measure input responses from different directions. So we don't need only mono-aural microphone that we have, of course, because the standard ISO 3382 asks for this microphone. The ISO asks also for the binaural measurement if you want to calculate other parameters called interaural cross correlation. So the similarity between the two input responses inside our cochlea, inside our ears. But we have no possibility to calculate other spatial parameters, even if we use the Ambeo, so the B format, that is similar to a figure of 8. We can, by post-processing, to simulate the behavior similarly to a figure of 8 microphone. So we are able to calculate parameters like lateral fraction and lateral efficiency. And moreover, the most important aspect is we are able to capture the sound coming from all the directions by means of the Egen mic. So now we are moving to the other room, and I will go on with this lecture in an interactive way. So I will help you, I will ask you help for me, so to help me to mount everything. And in the meantime that we mount everything, I will tell you what we are doing, because this is very important to make practice of this. Remember that tomorrow we will make the measurement exactly with this equipment. I forgot one important thing, that for having the possibility to understand the direction of the sound with the Egen mic, we need also to take a picture of 360. So this is the reason why on the top you can see the camera 360, because we will plot over the picture some maps in which you can understand where the reflections are coming from. This is what we are going to do. Okay? So I think that for now we can stop. We are 4 minutes delayed. We have some problem. I'm sorry, because I believe that we were not able to record with Zoom, but we have the plan with the camera. Yeah, we have that problem with it. Okay, so I think we can move immediately. Yes.
Ne, samo ovo ostane. Ok, može. Ja ću ovo poglasiti.
Što molim?